In the coming years, the increase in air traffic will automatically lead to an increase of the number of flights at a given airport. Aviation experts estimate that in the coming 20 years, around 60% of the top 100 airports will face congestion. Due to various reasons, it becomes more and more difficult to expand airport infrastructure, such as constructing new runways. For this reason, airports have to optimize the utilization of runways so as to be able to cope with future traffic growth. This is the objective of SESAR Solution 1411, dynamic pairwise separation based on airborne runway occupancy time prediction. This solution is developed by Airbus in the frame of SESAR 2020 Wave 2. Currently, aircraft are separated on final approach by the air traffic controller. Before clearing an aircraft for landing, the air traffic controller has to ensure that the runway is free of any aircraft. The separation to be applied on final approach depends on several factors, such as wake vortex or minimum radar separation. Wake vortex separation accounts for 10 to 25% of the separation factors at typical busy airports in Europe. When there is no wake vortex constraints, separation is mainly related to the minimum radar separation value, which can be adapted depending on runway occupancy time. As a consequence, if the lead aircraft decelerates too quickly, it may spend too much time on the runway, and the following aircraft would then be forced to go around. The same would apply if the lead aircraft misses the runway exit the pilot intended to take. With current procedures, as the time each aircraft will spend on the runway is not known in advance, the separation between arrival aircraft includes a buffer to account for this uncertainty.
Runway occupancy time is a true concern primarily for capacity-constrained airports. Airlines operating at those airports are affected by the snowball effects of congestion such as delay, holding, or slot limitations. This is particularly true for the main airline at a specific airport, which market increase depends on the runway capacity optimization.
This new airborne runway occupancy time prediction function, developed by Airbus, will lead to a safe reduction in final approach separation.
In today's operation, pilots operating under high-intensity runway operations are familiar with vacating the runway as soon as possible. They implicitly know which exit they would take based on experience. With the new airborne AROT prediction function, a new task will be needed during the descent and approach preparation phase, shortly before the top of descent.
The pilot will be requested to enter some information on the runway exit he intends to take after landing. Then, based on the landing settings and aircraft configuration, the system will automatically predict an associated ROT. This predicted ROT value and the runway exit intention will then be automatically sent to the approach control center using ADSC. This will allow the controller to safely optimize the separation behind the aircraft. The pilot will then perform a landing as per current procedures using the existing Autobrake system. Thanks to this reliable runway occupancy time prediction, the separation can be safely reduced. The separation value can be optimized depending on the predicted ROT sent by the aircraft, in this case leading to a time separation of 55 seconds. With the current rule, a separation of 65 seconds will be applied behind the same aircraft, as the ROT is not known. This optimization in separation would lead to runway capacity benefits ranging from 0.5 to 1 movement per hour.
This runway occupancy time prediction function brings various benefits. We are moving a step further with this optimization of runway capacity based on a reliable airborne prediction and on the collaboration between the aircraft and the air traffic control. This leads to a more sustainable utilization of the existing infrastructure, delaying the need for new runways. As a snowball effect, delays can be reduced, leading to fuel burn and CO2 emissions reduction.